Okay, so now we'll prove a new theorem. Let X together with some metric D be a metric space. And define a function rho mapping ordered pairs of the set X into non-negative real numbers by rho of xy is the smaller of two values, and those two values are the distance between x and y under the metric D and 1. Then rho is a metric on the set X called the standard bounded metric corresponding to the metric D, and this metric rho induces the same topology as the metric D. All right, so this is a two-part theorem. First, we need to show that rho is a metric, and then second, that this metric induces the same topology as the original metric D in the metric space. Now, non-degeneracy and symmetry are obvious. So we will show that the function rho satisfies the triangle inequality. And we'll look at several cases at once. If the distance from x to z is greater than or equal to 1, or the distance from z to y is greater than or equal to 1, then either rho of xz is equal to 1 or rho of zy is equal to 1. Again, because rho is the smaller of the values of either 1 or the distance from x to z. So if the distance from x to z under the metric D is greater than or equal to 1, then rho is equal to 1. And this is true for the points xz and zy. So the sum rho of xz and rho of zy is greater than or equal to 1. And since rho of xy must be less than or equal to 1, we have that rho of xy is less than or equal to the sum of rho of xz and rho of zy. So we looked at several cases at once in this statement. If either the distance from x to z under the metric D is greater than or equal to 1, or the distance from z to y under the metric D is greater than or equal to 1, then the triangle inequality holds. So now we have to look at the case where both the distance from x to z is less than 1 and the distance from z to y is less than 1. So if the distance from x to z is less than 1 and the distance from z to y is less than 1, then rho of xz is equal to the metric, the distance from x to z under the metric d, and rho of zy is equal to d of zy. Now, as d is a metric, we have that the distance from x to y is less than or equal to the sum of the distance from x to z and from z to y under the metric d. And by definition, rho of xy is less than or equal to this distance from x to y under the metric d, because if d of xy is greater than 1, then rho of xy is equal to 1, and if it's less than 1, then they are equal. So we have that rho of xy is less than or equal to the sum of the distance from x to z and from z to y under the metric d, but this is exactly equal to rho of those points. So rho of xz plus rho of zy. So in any case, the triangle inequality holds. And hence rho is a metric on the set X. All right. So now we need to show that rho induces the same topology as the original metric D. Now the collection script B consisting of open balls for each point x in the set X, and choosing the positive radius epsilon to be less than 1 is a basis for the metric topology, or on X. Now, since we have chosen the radius to be less than 1, the metric D and the metric rho produce the same open balls. That is, the open ball under the metric D centered on X and radius epsilon is exactly the same as the open ball under the metric rho centered at the point X with radius epsilon. So the two topologies, rather the two metrics produce or induce the same topology. So given any metric space, then the metric space consisting of X and the metric rho, where again rho is the minimum of the two values, being either the distance from X to Y the distance from X to Y under the metric D, or 1, is a bounded metric space. And as we just demonstrated, it induces the same topology. Now, the theorem was an existence theorem, not a uniqueness theorem. If XD is a metric space, then the space consisting of X in the metric row, where rho is the ratio of the distance under the metric D to 1 plus the distance under the metric D, then this metric space is also a bounded metric space. Since rho of xy is less than 1 for every pair of points x and y in the set X. Right? So next we'll show that metric spaces are Hausdorff. Let X together with some metric D be a metric space. Then the topological space with the metric topology is Hausdorff. Okay. Now, the point X is in the open ball centered at X with radius epsilon, and the point Y is in the open ball centered at Y with radius epsilon for any choice of radius epsilon, but we will specifically let epsilon equal 1/2 the distance from X to Y. Then as these open balls are open sets containing the respective points, they are open neighborhoods of the points X and Y respectively. So we'll show that the intersection of these two neighborhoods is empty. Now the intersection of the open ball centered at X with radius epsilon and the open ball centered at the point Y, radius epsilon, is the intersection of two sets, and that is the set containing the points Z in the set X, such that the distance from X to Y, X to Z, is less than epsilon, intersected with the set of all points Z in the set X, such that the distance from Y to Z is less than epsilon. And so this is the set of all points Z in the set X, such that the distance from X to Z is less than epsilon, and the distance from Y to Z is less than epsilon. And so we have that the distance from X to Z plus the distance from Y to Z, but as the metric D is symmetric, we also have the distance from Z to Y, is less than twice epsilon. Now we chose epsilon to be half the distance from X to Y, and so we have that the distance from X to Z plus the distance from Z to Y is less than twice of half of the distance from X to Y. And so we have that the distance from X to Y is greater than the sum of the distance from x to z and the distance from z to y. But as d is a metric, we have that the distance from x to y is less than or equal to the sum of the distance from x to z and from z to y. And so the intersection of the open ball centered at x with radius epsilon with the open ball centered at y with radius epsilon is empty. And again, this was for the choice of epsilon being 1/2 the distance from x to y. And as this is a non-zero number, half of that is a non-zero number. And so this is a valid radius, a valid choice for epsilon. And for this choice, there exist open neighborhoods containing the points x and y respectively, such that the intersection of those neighborhoods is empty. And so the topology, or specifically the metric topology, on x induced by d is Hausdorff. The space is Hausdorff. All right, so next we'll prove a theorem concerning subspaces of metric spaces. So let the set x together with some metric d be a metric space. And let the set A be a subset of the set x. The topology induced on A by restricting the domain of the metric d to Cartesian product of A with itself is the same that the set A inherits as a subspace. All right? So let d sub y denote the restriction of the function d to A cross A, a basic open set for the topology generated by d sub y is an open ball with that metric d sub y. This is set of all points y in the set A such that the distance under this restricted function from x to y is less than epsilon. Now this is the same as the set of all points y in A such that x is in the set A and the distance under the metric d from x to y is less than epsilon. Now a basic open set for the subspace topology on A is A intersected with an open ball in the set X where so this is an open ball. And the space X. So the intersection of the set A with an open ball in X is the set of all points Y in the set A such that the point X is also restricted to the set A, and the distance under the metric D from X to Y is less than epsilon. And this is the same as the open ball with the restricted metric centered at X with radius epsilon. And so the two are the same. The subspace topology on A is the same as the metric topology induced on A by the restricted metric.